convert from polar to rectangular. So that'll be what we start with today, but the other way, okay? From rectangular to polar. In rectangular, what are the two letters that they give you in a rectangular coordinate?
X and Y.
Right. They give you an X, they give you a Y, and what do you have to convert them to be polar?
Radius and theta.
We got to convert it to a radius and an angle. Radius and theta. Right, so let's sketch it out as a rectangular coordinate, assuming they give us an X and a Y. So if they give us an X and a Y, we basically have something like this. From this point down, that's my Y. That's the height that I went up. From this point over, that's my X. So they're going to tell me those two things. I have to figure out the R and the theta. Where would the R be in that picture?
The hypotenuse.
Yeah, it would be the hypotenuse of the triangle. Because if you think of that point, don't think of it as XY. Try to start thinking of it in polar, because that's what we're changing it to. Think of it as being on the edge of a circle. You draw a line from that point to the center of the circle. That is the radius of the circle, and it's the hypotenuse of that triangle. So how do you find, and we'll write it down in a second, but how do you find the hypotenuse if you know two other sides?
Yeah. A squared times b squared equals c squared. Oh, a squared plus b squared equals c squared.
Yeah, and what is that?
Pythagorean theorem.
The Pythagorean theorem. Yep, so we're going to use that to find the hypotenuse, which is going to be my R. Now I need to find my angle. The angle is what's between the hypotenuse and the X, the blue line. That's here. So you need to find this, and you're going to know that, and you're going to know that. So what trig function could you use? Think about what position is this side?
Adjacent.
That's adjacent. And what position is this side?
That's opposite.
That's opposite.
Opposite over adjacent.
So if you wrote that down, tangent would equal what?
Opposite over adjacent.
Yep, so y over x. But now we've got to get tangent, we got to get rid of tangent, and we got to get theta by itself. So how would we get theta by itself?
Inverse tangent.
Yep, and we'll write that down nice and neat on the next page. Okay, but that's basically the two things that you need to convert to polar. You need the Pythagorean theorem for the radius, and we're going to need inverse tangent for the angle. All right. Now, it is important that we know what quadrant the point is in. Okay, in this case, it's quadrant 1. You'll see why the quadrant's important in a second. So if you can determine what quadrant you're in without graphing it, that's fine. The point of step 1 is just to figure out your quadrant. Then, if you are in quadrants 1 or 4, which we were in this last picture, that's quadrant 1. If you're in quadrants 1 or 4, you can do the inverse tangent of y over x. That's the formula we came up with on the other page. That works fine. The problem with inverse tangent is it doesn't work in quadrants 2 or 3. It doesn't work over here. Because when you do inverse tangent, you always get an answer between negative 90 and positive 90. That's what inverse tangent always gives you an angle of. Where's negative 90 on this diagram?
That would be the down.
Right, it's the same as 270. So this is negative 90. Where's positive 90? That's up. So inverse tangent always gives you an answer between here and here. What two quadrants is that?
1 and 4.
1 and 4. So it only works in 1 and 4. To make it work in quadrants 2 or 3, we just have to make a small addition to it. In quadrants 2 and 3, you have to add pi if you're doing radians, or 180 if you're doing degrees. And essentially what that does is it takes the answers that you were originally getting on this side and it flips them over, and now we can get answers on that side. Okay, but that adding pi or 180, that's only in quadrants 2 or 3. Yes?
I just want to blow that.
So these two formulas cover everything that you need to do if you are in quadrant 1, 2, 3, or 4.
What if you're in quadrant 5?
Well, there's no quadrant 5, but there is another location besides quadrants 1, 2, 3, and 4.
Origin 0.
Well, we're always going to have a point. Well, I guess you could have the point 0, 0. So where is that? It's not in a quadrant. It's
On the edge of quadrant.
and what do you call the things on the edges of the quadrants?
Axis.
The axis. Yeah. So if you are on an axis, these formulas won't work. Think about this point right here. What's the x value of that point? 0. I don't know the y value. It's up. But the x value is definitely 0. What happens if you try to plug in 0 for an x value into either one of those formulas?
It's going to be 0. Oh, wait, never mind.
It would be undefined because you'd be plugging 0 in for x. That's dividing by 0. You can't do that. So those formulas only work when you are in a quadrant. If you're on an axis, you have to memorize that it's one of those 4 answers. 0, 90, 180, or 270. Okay, and now that covers everything we need to know about the angle, whether it's in a quadrant or on an axis. Okay, if it's on an axis, it's quicker to find. Okay. All right, so that's how you find your angle. And what's the other thing we have to find when we're writing a coordinate in polar?
Your radius.
Yep, we need the radius. And remember, that's like the Pythagorean theorem. You're going to know the x, you'll know the y, and you're going to solve for r. So x squared plus y squared equals r squared. All right, so we'll try a couple examples, and then that'll be it for 5.1. What's that?
Today was a short day.
Yeah, well, we got one more thing we're going to do after 5.1, but that's it for 5.1. Yeah. We're going to do that A4 in the back of the book. All right, so it says convert -2 to polar. Okay, so first step, identify your quadrant. What quadrant are we in? Yep.
Quadrant 4.
Yeah, you're right 2 down 2, so somewhere right about there. Whether you do theta or r first, it doesn't matter. Let's do theta. What's the formula for theta if you are in quadrant 4?
Inverse tangent of y over x equals theta.
Inverse tangent of, and what's y in this case?
Y is -2.
-2, and x?
2.
2. So it's really just the inverse tangent of
-1.
-1. Okay, so inverse tangent of -1, and that's radians. But if we want degrees, okay, we get -45 degrees. So there's our angle. Now we need to find the radius. Okay. What's the x? Well, what's the x value?
2.
Yeah, this has a distance of 2. And then what's the distance from here to here?
-2.
Well, it's a distance it's down 2, but it's still 2. So if you use Pythagorean theorem, what would the right-hand side look like when you set that up?
4 plus 4. Well, afterwards.
So 2 squared plus 2 squared. So that's going to give me 8. So that makes the radius
Or no, so that's square root of 8.
the square root of 8. And if they ask us to simplify that square root, what does the square root of 8 reduce to as an exact answer?
2.
What is it?
It's either 4 root 2 or 2 root 4. I think it's 4 root 2. I don't know.
2.828.
So we're not looking for a decimal. We're just looking at
2
reduce
square root
that.
of 2.
Yeah, 2 square roots of 2.
Ah.
Is there any question on how to get that? 2 square roots of 2. You can break it up into square root 4 times square root 2. And then the square root of 4 is 2. So it's 2 square roots of 2. All right, so let's write our final answer. So r, comma, theta. Now, when we talked about polar coordinates yesterday, we said that if a point is not on the polar axis, how many different ways are there to write it? How many?
Is it 4?
4. Yeah, there's 4 different ways. So this is go right and then go clockwise. What if I wanted to go right and go counterclockwise?
You would leave it.
What's negative 45 the same as?
35.
In radians?
No, in degrees.
Yeah, 135. 30.
So we've got to land right here. So instead of going this way, you're going to go
315.
that way. 315.
315.
Okay.
Yeah. And there's 2 other ways we could write that answer as well. If they're looking for to convert it to polar, and they didn't specify anything more than that, then any of those 2 answers are fine. But they might say in the directions, leave your answer with a positive angle. Okay, or leave your answer with, they'll tell you what they want. So any question on how we got either of those? Once you get one of them, then it's easier to get the others. But you just have to figure out one of them first. All right, let's try this one. -4, -5. Okay, what quadrant is that one in? That's in quadrant 3. We don't need an exact sketch. We're not trying to really sketch it. Okay, but we know it's quadrant 3. What is the formula for theta in quadrant 3? And let's do it in degrees. Yep.
In degrees?
Yep.
180 plus inverse tangent of y over x.
So in this case, it's inverse tangent of
Y over x.
-5 over
-5 over -4. So now we can just cancel the negatives. So it's 180 plus the inverse tangent of 5/4. It's 231.3. We'll call it 231.34. Since we rounded the angle, we might as well round the radius as well. Okay, so what's going to be my formula to figure out my radius? Plus -5 squared. So that's going to give me 16 plus 25. What's 16 plus 25? 41. And to get r by itself,
Or,
Square root. of-
square root.
Square root.
Take the square root of 41. So we get
that's
about,
two different things. Square and square root is two different things.
so we get about 6.40. About. All right. When we write the actual coordinate now, which number goes first?
6.4.
Yep. So the radius, comma, and then the angle. And remember, there's 4 different ways they could write that. They could do both positives, both negatives, or one of each. I would say, positive is probably pretty common. So any questions on converting from rectangular to polar? All right, so that's 5.1. Okay, so, what's that?
It's weird.
You like the squares?
Didn't we do that at the beginning of the year?
Rectangles?
Right.
No? We might have done this a little bit.
I think I have it in my notebook.
We could have talked about this maybe the first or second day.
I got it.
Yeah, that's it. We're just going to kind of do a refresh on that. But yeah, we did this very, very early on. So we're going to be looking at complex numbers. But what I want to do is kind of see, where do complex numbers fit in to like the numbers that we're used to using. So I'm going to start with the simplest kind of numbers that we use, and then work our way out till we get to complex numbers and see where they fit in. So the simplest kind of numbers you can have. They don't include they don't include negatives, don't include fractions, don't even include zero. You pretty much just use if you want to figure out like how many of an item you have. Does anyone remember what you call those numbers?
Irrational. Oh, wait, which
That's going to be quite a ways later. Those
probably counting.
counting, right? Those are the simplest kind of numbers you can have. Now, let's say that that's the only kind of numbers we understand. Numbers that start at 1 and go up. No fractions or decimals. If I took, somebody give me a counting number.
2,
2, all right? And then give me another counting number.
3.
3. If I take those 2 counting numbers and add them up, do I get a counting number?
Yes.
Yeah. What do I get? 5. Let's try something else. Let's take the same 2 counting numbers. Let's multiply them. If I multiply 2 times 3, do I get a counting number? Yeah. All right. Let's try something else. Let's try taking the same 2 counting numbers and subtract them. Okay. If I subtract 3 from 2, do I get a counting number?
No.
No.
Integer.
You what?
Integers.
No, negatives, you never count with negatives. Like, you wouldn't go like -3, -4, -5. You don't count with negatives. So, in this case, if all we understand is counting numbers, then we have to say this is undefined. We'd say, well, there's no way that you can take away more than you have. So, unless we're going to invent a kind of number that allows us to do that, we can't do it. All right? We can't even do this. We can't even do 2 minus 2. 2 minus 2 is not a counting number. So if somebody didn't know the number 0, then they would say, well, 2 minus 2, I'm not sure. I don't know what number that would be because they don't know 0. So to fix that, we invent basically what we call whole numbers. The only difference between whole numbers and counting numbers is now you have the number 0. So whole numbers let you do some more types of math, okay, more arithmetic. More than just counting. With counting, you'd never need the number 0 because if you're counting objects, that means you have something in front of you to count. If you're not counting them, then you wouldn't be counting them. Does that make sense? right? If you've got objects in front of you, you're going to be counting 1, 2, 3. You don't start with 0 when you count. You don't need the number 0. But even by adding the number 0 to our knowledge of numbers, we still can't do this problem. We have to invent another kind of number to do a problem like this. And what kind of numbers do we need to do that kind of problem?
Integer.
Yeah, we need integers because integers have what in them? They have negatives. All right, so now we start with integers, we start to get into the idea of negative numbers. Okay, if you wrote that down for somebody in first grade, 2 minus 3, they'd probably say you can't do that. They'd probably say that's impossible. No, it doesn't work. Or I don't know. They wouldn't know what to do because there's no concept of taking away more than you have. Right? And it's not that you can't do it. It's just that they don't have a way to write a number that represents a negative. They don't know that yet, right? So now with integers, it allows you to do a little bit more. Okay? You can deal with negatives. So we took counting numbers and we added them, we subtract them, we multiply them. Can anybody think of something we could do with 2 and 3 that wouldn't even be an integer? Yeah?
Rational.
Yeah, we could try to divide them. Okay, when you're first learning division, you never do something like that because 3 doesn't go into 2. So somebody that was just learning about division would say that's not possible. And they may liken it to saying, all right, if I had 2 objects, I need to split them to 3 people. You can't do that. If you have 2 things, you can't give them out to 3 people. But we know you can do that if you start breaking things into fractions. Pieces and parts of a number, not a whole number, but now we get into, what did you call them?
Rationals.
Rational numbers. And for most everyday kind of math, I would say rational numbers probably cover everything you do. A lot of times, you buy something, very rarely does it come out exact, right? If you get gas, you might get $30.42. That means 42 hundredths of the next whole dollar, right? It's a piece of the next dollar. Another place might be like cooking. Right? Maybe you're making a recipe and you don't need 2 cups of flour or 3 cups of flour. You need something in between, 2.5 cups. So it's a fraction of the next number. So rational numbers are basically numbers you can write as fractions. Does anybody know the numbers that you can't write as fractions, what those are called? Yeah?
Irrationals.
Yeah, those are irrational. Once you get into irrational numbers, now we're starting to get more theoretical, right? Irrational numbers are numbers like square root of 2. For most purposes, if you had a calculation and it involved using the square root of 2, you're just going to round it, right? Most people are not going to take the square root of 2 and use, I was just going to show you all the decimal places, as much as I can. They're not using that many decimal places. I mean, even if you were machining a part, you had to be really, really accurate. Maybe you're going tenths, maybe thousandths or 10,000ths of an inch, but you're not going out to that many. There's no machinery that can make something that accurate. It's just too much. So we round it. All right. Other numbers that are irrational are numbers like pi. Even pi, for most purposes, you're just calculating area of a circle or something like that. You could probably get away with 3.1415. It's probably close enough for most things. You're not really going to need that many decimal places. All right, so now if you take all the numbers that you can write as fractions and all the numbers you can't write as fractions, those are called real numbers. Real numbers are what you study in Algebra 1. Okay? Everything you do in Algebra 1 is a real number answer. But just like trying to take away more than you have, or trying to divide two things where the one number doesn't go in evenly, there's another kind of calculation we can do that doesn't fit into this system. Something like this. Square root of -4. If you don't know the next kind of number system I'm going to write down, then you would have to say this is impossible. Just like somebody that doesn't understand negatives would have to say that's impossible. But it's not impossible. It's just you might not know how to write the answer, but it's still doable. Does anybody know what kind of numbers you need to do a calculation like that? Yep.
Imaginary numbers.
Those are imaginary. Now we're really starting to get theoretical. Okay, 2 minus 3, that's a pretty practical problem. I mean, you could think of situations where you might have to take away more than you have in real life. Like if you have, $50,000 in the bank and you want to buy a house that costs $200,000. Well, you're taking away more than you have, so you're going to need a loan. You're going to be in debt. Right? That makes sense. Applications for these kinds of problems, we're getting more into things that I know in engineering, they might use complex numbers, but that's really the only application I've ever seen, engineering. So if you're not doing that kind of stuff, you probably aren't going to be doing square roots of negative numbers. So those are examples of imaginary numbers. 3i, -2i, square root of -4. So where does complex fit in? Well, complex is all of that. Okay, so complex numbers are basically this whole thing. All the reals and all the imaginaries. That's the complex number system. So technically, even in Algebra 1, every number that you deal with is a complex number. It's just the imaginary part is usually 0. You don't have an imaginary part. And that's what we're going to talk more about right now, okay, complex numbers. So complex numbers are made up of two parts, a real part and an imaginary part. And when you write a complex number, the way that you usually do it, if you do it in what's called standard form, you put the real part first, and you put the imaginary part second. And again, that's called the standard form of a complex number. Okay, as far as what we're going to do with complex numbers, we're not really going to get into applications. We don't do that. All we're going to do is basically add, subtract, multiply, and divide. Okay, the next step would be looking at how could you apply it. But most of those applications are kind of a little bit beyond what this class would be about.
Thank you.
Okay, so there's an example of a complex number. 2 plus 3i. Using the information above, what is the real part in that 2 plus 3i?
A.
Well, it's 2, yeah. And what specifically is the imaginary part? 3, yeah. So the real part is 2, and the imaginary part is 3. What if I wrote something like this? 5. What's the real part there?
It's
5. And what would be the imaginary part?
There's none.
There isn't one. So what do you think we would put for it?
Would you put an I next to it still, or no?
So
But you wouldn't do that because it would make it imaginary then.
so what do we think the imaginary part is then? It has to be some number there for the imaginary part.
1.
No, there's not a 1 there. If we put plus 1i, then that means the imaginary part is 1. And it's not 1 in that one. Any other guess what the imaginary part is?
Resolution? 0.
0. The imaginary part is 0. So when you see the number 5, it's the same thing as writing this. 0i. We don't normally explain that in Algebra 1 because that would just confuse Algebra 1 students. We just write 5. But really, it's 5 plus 0i. Yeah. Yeah. Okay, if a number does not have a real part, okay, like 4i, negative 2i, okay, that is called a pure imaginary number. That's a number without a real part. It's a pure imaginary number. All right, so equality of complex number. What is that? Yeah. So when we write a complex number, how many parts did I just say it has? 2. The first part is the real, and the second part?
Imaginary.
Imaginary. So let's say we have these 2 complex numbers. I don't know what the A, the B, and the C, and the D are. But I know that A and the C are the real parts, and the B and the D are the imaginary parts. Normally, when you say 2 numbers are equal, you only have to check one thing, right? Like if I had a box here and a box here, the only way what's in both of those boxes could be the same is if you had like a 2 and a 2. You just have to check that number and check that number. Well, with complex numbers, there's 2 things you have to check. You have to check that the real part here matches the real part there. And then you have to check the imaginary part there matches the imaginary part there. So let me write this down. So those 2 complex numbers are equal. I just want to kind of shorten that. If that up a little bit. So those 2 complex numbers are equal if the real parts match, the A and the C match, and the imaginary parts, the B and the D. All right, so let me make up an example of 2 complex numbers that are equal. Let's say, I don't know, 3 plus 2i and 3 plus 2i. Those are equal complex numbers because this part matches that part. This part matches that part. Now, what if I did this? Are those equal?
No.
No, they're not. We don't even say like they're partially equal. No, they're not equal. Right? The real parts are equal, but the imaginary parts are not. So these are 2 totally different numbers. It's kind of like looking at the number 12 and the number 14. You wouldn't say that these are partially equal because there has a 1 here and a 1 here. No. 12 and 14 are different numbers. Okay, they're just different. Okay, same thing here. Any question on that idea? Okay, so how do we add two complex numbers together? Well, you kind of think of it as combining like terms. Real parts can only be combined with real parts, and imaginary with imaginary. Okay, you can't combine a real with an imaginary. That's why when I write 3 plus 2i, 3 is real, 2i is imaginary, there's no simplifying that. It's not like you can put it together and say 5i. No. Or 5. That doesn't work. Okay. So to combine two complex numbers with adding, you can add the real part for each complex number, the a and the c, and the imaginary part, the b and the d. Just remember, when you combine the b and the d together, put the I next to it so we know it's imaginary. All right, so let's try a couple examples where we just add two complex numbers together. So 3 plus 8i and 8 plus 2i. We're going to add them up. Okay. When you combine those two complex numbers together, what are you going to get for the real part?
11.
11. Yep. You're going to get 11. And what are you going to get for the imaginary part?
10, 5.
Yep. So it's 11 plus 10i. And I know we've just been using I as kind of this symbol. I'm going to talk more about I, just I, in a minute. Okay, it's kind of important we understand what I is. I know you think I is a letter, and it is a letter in the English alphabet. It's not a letter right there. Okay. Any more than when you write this in math. That is never a letter in math. Like if you had to pick a variable for a problem, you wouldn't pick this Greek letter as a variable, ever. Because it already stands for something. What does that stand for? Yeah, it has a meaning to it. So it has a meaning of 3.14. Same thing with I. I is not a letter here any more than that would be a letter in math. It is a letter in the Greek alphabet, but we don't use it as a letter in math. Okay, so we'll talk about what I is in a second. All right, let's try this one. So 4 minus 2i plus 3 minus 8i.
The real part would be 7.
So the real part would be 7. And then negative 2i plus negative 8i.
Negative 10i.
Negative 10i. That's what you get when you add those up. Yeah. Yep, this here. No. Right. And this one. Negative 3 minus 4i plus negative 7 plus 8i. What's going to be the real part when you put those together?
Negative 10.
Yep. So you negative 3 plus negative 7. Make sure when you write these, because you're using I a lot, make sure you don't accidentally confuse your I with a 1. So I'll try to make my 1s very clear. Okay, so negative 10. And what about the imaginary part?
Plus 4i.
Yep, negative 4i plus 8i. Negative 10 plus 4i. Okay. Any questions on that? So difference. Well, if we can add, we can also subtract. When you're doing a difference, think of it as like a distributive property. You're going to subtract C from A. minus the c. And then you're gonna minus the d from b. So it's like distributing that negative out. So it's a minus c, b minus d. And then put the I next to the b minus d so we know it's imaginary. Okay, let's try that one. So we got 4 plus 12i, and you're going to subtract 3 plus 4i. Okay, anyone think they could give me the whole thing, final answer? Yeah.
1 plus. Oh, wait, no, wait, hold on. Okay.
It's gonna be 1 plus 8i.
Yeah.
Yep.
All right, so I had it right.
So 4 minus 3, that's going to give you the real part. And then 12i minus 4i. 12 minus 4, 8i. Yep.
Thought it was a minus in between. I was like,
Yeah, we're going to do one in a second where we might end up with a minus in between. Or maybe we won't. We'll see what happens.
let's do this one.
All right, so we got 3 minus 5i. And then we're going to subtract 8 minus 6i. Now, all the rules we know about negatives still apply. So keep that in mind as you do this one. Yep,
Can I answer it?
sure.
It's going to be negative 5 plus. Give me a second. 1i.
Yep, negative 5 plus 1i. If you don't want to put the 1, you don't need it. You can just put negative 5 plus I. Because it's negative 5 minus 6. So it becomes negative 5 plus 6, which is 1. Okay. Any question on that? All right, so what is this I, right? We keep using this as a symbol. And I told you that in the context of complex numbers, this is not a letter. It is a letter in the English alphabet, but we're not using it as a letter in math. It is a number. It's basically like writing this. When you write negative 5 plus I, that's what you just wrote. Negative 5 plus the square root of negative 1. So that should kind of tell you what I is. What is I?
Negative 1 square root of negative 1.
It's the square root of negative 1. And that's not something you can prove, right? Like if you said you gave the Pythagorean theorem and you said, well, I don't understand why that even works. I could prove that to you. I could show you why a squared plus b squared equals c squared. I can't prove to you why I equals the square root of negative 1. It's a definition. It's not something that can be proven. In geometry, that would be similar to saying that parallel lines don't cross. You can't prove that because the word parallel is defined to mean they don't cross. It's a definition in geometry, right? Parallel lines don't cross. So it's the same thing here. So I equals the square root of negative 1. Why did they pick I? I don't know. They could have picked anything. They could have used a Greek letter. They could have used something other than I, but everyone agreed to let this calculation be equal to that symbol for whatever reason. Now, this we can show why this is true. I squared. If we take I and raise it to the second power, okay, what did we just say up above I is?
Negative 1. Square root of negative 1.
It's the square root of negative 1. And now raise that to the second power.
Negative 1.
Right. When you square and square root, those two things cancel. So I squared is the number negative 1. And that's important because anytime we do a calculation and you have an I squared in it, which comes up when we do multiplication tomorrow, You cannot leave I squared in the final answer. You always have to change I squared to a negative 1. And we'll look at that more with I squared tomorrow. Okay, so any questions on that? Okay. So the first part of the homework, that's on converting from, what did we do today? We did rectangular to polar. And then the second part of the homework is just a few adding and subtracting complex numbers. So 308, 55 to 65 all, and 560, 9 to 14 all. Okay, so we'll look at that tomorrow. There, I think if you go to the homework for tonight, there might be 2 different PDFs in the homework, or I might have put it all together as one. But you got a little under 20 minutes. So if you want to check it out and you're not sure what the homework is, you'll see it on Schoology. It's right below the one you did last
Check
time.
this out.